It's time to make sugar cookies. Set the temperature to 375 degrees Fahrenheit, and then you're going to want to grab yourself a nice oven baking sheet, and then you're going to want to use some sort of nonstick spray. Butter also works, neutral oils work, just something to make sure the cookies don't stick once they're finished. And then we can just place that on top of the oven because we don't really need it right now. Next, we're going to focus on making the flour mixture, and we're going to start that with 1.5 cups of flour, pre-sifted if you're able. And then we're going to do 1/2 teaspoon of baking powder, and then we're going to do 1/4 teaspoon of baking soda. And then we're also going to finish with salt. Pretty generous amount. We're going to mix that together. Now, jumping back to the baking soda, that is pure sodium bicarbonate, and what's really interesting is that increases the basicity of the solution and of the cookies. This allows more nucleophilic attack, and as we will learn about the Maillard reaction, this will ultimately increase the amount of products in the Maillard reaction and lead to more browning. So now we're going to cream together the butter and sugar. A useful tip is to try and melt the butter beforehand in your hands. We're going to use a full stick of butter and about 2/3 of a cup of sugar. And we're going to try and cream that together. Now, unfortunately, despite the old butter in the hands trick to sort of help melt it, the butter that I used was still pretty stiff at first. That's not a big deal. It will cost you a little bit of extra time, and it might be a bit harder to work with. But butter fresh out of the fridge could be used, but try and melt it as much as you can beforehand just to make it easier to work with. Ultimately, as you cream the butter together, you're probably going to need to try and scrape the edges as much as you can, and you'll know you're good once the edges come off clean. There shouldn't be any large amount of sugar sticking to the edges, because that's a sign that you haven't fully incorporated everything. So I'm just going to speed that up now because it did kind of take me a while. And then I'm going to add a small amount of vanilla and almond extracts just to sort of give it some of those beautiful smells and a tiny pinch of flavor. And then I'm going to mix those together and also add the egg. And with that, that's all the ingredients we need. And then we're going to mix those all together. Fortunately, the egg will help melt some of the butter and overall just make it more easy to work with. And then once we get that well combined, we'll be able to move on. Don't eat that. That's not good cookie dough. Once we add the flour in, it will actually be very good cookie dough. Of course, you can't really eat it because we did just add raw egg, but otherwise it's alright. So you're going to want to add small portions of flour to start with, probably about 1/2 cup at most, and then you're going to want to continue to mix it into the butter until you really start to get a dry cookie dough consistency. If you're following the recipe, you will use all of the flour ultimately, and a pro tip would be that once you get to about 1/2 of the flour used and you get everything incorporated in the mixing bowl, you can generally pour in most, if not all, of the remaining flour and get it mixed together, which you can see me doing here. I've got a small amount of flour left, and I'm just dumping the rest of that in. And even now, despite only 2/3 of the flour being added, we're still starting to see a sort of cookie dough consistency. You can test this by sort of getting some on your finger and really squishing it. If it sticks, it's probably not good. See how well it rolls. If it rolls well, it's nice and moist still. And then you can also roll it on the counter to make sure that it doesn't stick. If it doesn't stick, you're good. You can clean up your equipment. Try and get as much dough as you can, because it's good stuff. And then once everything's cleaned up, you're able to finally start making the actual balls of cookie dough. So I have a unique process where I use the 2 spoons and I spray them beforehand with Pam in order to reduce their stickiness, and then I use those to form the dough balls. Generally it is easier to work with your hands, but the spoons provide an advantage in environments where you don't want to be seen touching the food directly, given the current conditions and the current COVID-19 pandemic, it's very advantageous to avoid that as much as possible. And it just looks cool, quite frankly. Definitely do something if it looks cool and if it doesn't significantly affect your ability to actually do something. Another big advantage of the spoons method is that it actually helps you get more consistent sizes, just because you're only really getting what can fit inside a spoon. As you see on the side there, I'm rolling around these cookies in a sugar mixture. I'm actually using about a 1-to-1 mixture of sucrose to fructose. And sucrose, of course, helps create that nice classic crunch outer layer that we have in a lot of classic sugar cookies. Fructose is a unique addition, though. While it is slightly sweeter than sugar, and it is advantageous that way just because it has that nice extra sweet crust, fructose also undergoes caramelization at low temperatures. And this helps with the flavor, as we get some of these unique caramelization flavors that we wouldn't get if we just use sucrose alone. And we also get a little more browning from caramelization. Although, unfortunately, this is kind of cheating because it's not true Maillard. But it definitely looks a lot more impressive, and most people can't tell the difference. And it tastes a lot better with the fructose. So I'm going to continue to roll these cookies around in the dough coating and then add them to the pan. I originally wanted to do rows of 3, but as we find it out later on, I have 2 or 3 extra balls of cookie dough that just don't fit. As well, pro tip, when you're mixing around the cookie dough, you're going to really want to try and avoid carrying too much of the sugar over, because that can make the baking sheet hard to clean if there's stuck on sugar. This is probably the longest part of the cookie baking process, so if you do want to use your hands, you'll probably do it a bit quicker if it doesn't look as pretty and if you don't get as much. And now with the final cookie being added, we're going to move everything around just to get more even spacing, and we're finally ready to add everything to the oven. So here we are. We're going to make sure the oven's at the right temp, and then we're going to add them into the top rack. Top rack generally gives you the advantage of getting a more crispier outer layer. And of course with cookies that's very advantageous. We're going to set it to 12 minutes, and we're going to start doing some dishes. When things are sitting in the oven and just cooking, it's a great time to just do the dishes, or figure out anything else to do. Try to make yourself useful. Don't sit around and lose this valuable time, because if you don't use it, you will definitely lose it. While the cookies bake, we're going to talk about some of the underlying chemistry that helps change these pale and somewhat boring cookies into a beautiful experience of different flavors, and also the chemical basis for what causes the change in color of not only cookies but also breads and other meats. And the big reaction that causes almost all of this is the Maillard reactions. So starting, we have to look at the materials that we use to create the Maillard reactions. We need a reducing sugar, and we need an amino acid. We can also use the N-terminus of a dipeptide, and in terms of reducing sugars, we can use any form of sugar, such as monosaccharides to disaccharides to even polysaccharides. Amino acids are able to undergo this reaction using this nucleophilic NH2 here. So any amino acid, any polypeptide that has this free amino acid, either free N-terminus or the amino acid itself should have a free amino group. Any of these types of compounds will be able to undergo the Maillard reactions. In terms of sugar, we see 2 different enantiomeric forms of sugar here, D-glucose and L-glucose. And in terms of their properties, enantiomeric forms don't matter in terms of general reaction mechanism, but they do change the overall products. It's important to note that D-glucose is the only type of glucose that is normally digestible by the body. L-glucose is not. And the key to this, which will be described in more detail in the next slide, is this free carbonyl here in its straight chain form. what makes reducing sugars unique is that they have this free carbonyl in their linear form. And this is present in all monosaccharides, some disaccharides, and some polysaccharides as well. Any type of sugar in its linear form that has this free carbonyl can and will undergo Maillard reactions, assuming that there is also a protein or some type of amino acid present that can serve as a nucleophile. Moving on from starting materials, we're going to get to the real meat of the mechanism here with the Amadori rearrangement. So as discussed earlier, this amino acid here and this amine specifically will have a nucleophilic attack occur on that carbonyl. This will generate a tetrahedral intermediate here, and there will be a proton transfer that occurs that helps stabilize this NH2 and also protonate this OH. And then from there, this OH will grab the hydrogen and leave, forming water. And then this nitrogen will use the electrons left over from the bond to really double down and form a double bond between the nitrogen and the carbon in the sugar. From here, we form the glycosylamine. And again, we also gain water. From here, this glycosylamine will rearrange in order to form the Amadori product, where this pi bond here shifts down to a carbon-carbon bond and then ultimately shifts over to this oxygen, creating what we see here as the final ketone. Of course, this isn't the true final product in any Maillard reaction. This is just the big jumping point off that all the other materials occur. Full mechanism. So we looked at the 1-amino, 1-deoxy, 2-ketose product of the Amadori rearrangements. And from here, it can go through a variety of different mechanisms depending on the exact conditions, forming a variety of compounds, all ultimately leading to these unique compounds called melanoidins. These are generally brown nitrogenous polymers and copolymers. Usually they are aromatic, and of course, given their unique color, they're what creates the new colors in the Maillard reactions. Additionally, due to many of them being aromatic and generally unique, they have some new flavors that they bring to the party that aren't found in uncooked food, which is why seared steak tastes so different from, say, boiled steak. A lot of these compounds, for whatever reason, taste very good to us and are partly why we find these foods so enjoyable once they're cooked. Some of the general melanoidin products that we see are pyrazines. Pyrazines generally have cooked and toasted type flavors. We also have alkylpyridines. These tend to be bitter and burnt and are produced in larger number at higher temperatures or when you do let the food go burnt, which is why, of course, the food tastes more burnt because you're producing more of these compounds. We also have acylpyridines, and these kind of taste like cereals or sort of cracker-like. And it's interesting to note that this addition of the carbonyl group here completely changes the general set of flavors compared to the alkylpyridines. These small and what may seem subtle changes can have huge impacts on the final flavors and appearance of the food. And this is partly why food science can be so complicated. Moving down to the 5-membered heterocycles, we have furanones, and these are generally sweet and responsible for some of the caramel flavors found, although in some forms they can also taste slightly burnt. We have thiophenes next. These are meaty and roasted. Oxazoles are unique in that they have these green and nutty type flavors. They're one of the only compounds I've been able to find that actually have almost a sweetness to them, which is really quite unusual. Furans, of course, come in with their meaty and caramel-like flavors, and again, that might not be surprising considering the structural similarities between furans and furanones. And finally, we have purols, which are also cereal-like, similar to the acylpyridines here. And again, that's another interesting link that we see here. Despite this difference in structure, right, we have a 5-membered heterocycle, and then we have a 6-membered heterocycle. There are some key differences, and there are some surprising similarities, right? These are both aromatic compounds. They both have a nitrogen substitution in them, and yet they produce this very similar flavor in a lot of cases, which is very interesting. Unfortunately, this reaction, while useful, is also potentially dangerous. So here we have a similar mechanism as outlined above and after the Amadori rearrangement. We see down here a shift that generates CO2. Of course, that oxygen is deprotonated before CO2 is fully formed. And then we have this double bond formation here. And ultimately, after multiple steps, this will generate acrylamide, which is a cancer-causing compound and is one of the many reasons why you may hear people say that fried foods or seared foods may be slightly unhealthy to eat, because a couple of the compounds, especially acrylamide, that's probably the most notable one, will form under Maillard conditions and are known to cause cancer. Realistically, though, of course, this is a specific reaction between asparagine and glucose. And while asparagine is, a relatively common amino acid, the overall amounts of acrylamide that you're getting are relatively small. And quite frankly, if there is any measurable effect that this compound has, it's probably not going to be a very short-term one, which is why you can eat a lot of fried food over your lifetime and not necessarily see any ill effects. Ultimately, though, of course, personal decisions have to be made about things like that. It may be wise to cut out fried food if you are especially concerned or if you have a family history of cancer. But of course, fried foods are tasty, and generally speaking, raw food, for example, is far more dangerous than fried food would be. Interestingly, the Maillard reaction also occurs at lower temps, including inside our bodies right now. While the exact purposes and links of this reaction aren't fully explored, there is some early suggestions that it is linked to diabetes and cataract formation. So now that we're about 12 minutes in, the cookies are looking pretty good, but they're not quite as brown as I would like. So I'm going to add another 4 minutes. Still not quite done. After about a total of 16 minutes, I was able to take the cookies out. They were brown to the desired color, and they smelled quite delicious. So I took them out. I like the color that these have. The edges are brown while the insides are still white. Just to make sure that none of them stuck to the pan. And it looks like none of them did, so very fortunate in that regard. The pan came through. And you'll notice really here on the bottom, you see that unique browning and sort of speckled appearance that the cookies have because of those fructose crystals being stuck in there. So I've allowed the cookies to sit for a little bit, and now I'm going to split them up with my sister, and we're going to get a taste test. Kids are great for taste tests because they won't lie. If the food isn't good, they will say. They drop that too, so I'm just going to put that away. It's good. And as you can see, it's got a nice firm outer crust and a nice inner layer. It's a delicious cookie. And with that, I'd like to acknowledge the Elizabethtown College Department of Chemistry and Biochemistry, Honors OChem 2 for inspiring this project, Dr. James McKay for his guidance, and Joni Eisenhower for letting me use the Bowers Demonstration Kitchen for the live demo. I'd also like to thank Dr. Louis-Camille Maillard and Dr. Johnny Harge for their work, right? Of course, Maillard is known because he discovered the reactions, and Dr. Hodge really went in deep and was probably the first person to understand these reactions. Through their work, I've really been able to inform myself well about this and even improve my cooking a bit because of this. Thank you for watching. See ya.